puzzle where every task follows its own secret rule, you only get a few examples, and all the clues come as tiny colored grids. That is the ARC benchmark. Most researchers have treated ARC like a language riddle, converting these grids into text and letting huge language models reason through them. But this paper takes a different angle. It asks what happens if you see ARC as a vision problem instead. In this study, each puzzle becomes an image-to-image translation task. The grid is placed onto a larger canvas. A vision transformer processes it like a natural picture, and test time training helps the model adapt to brand new tasks with only a few examples. The surprising part is how far this visual approach goes, matching human performance when ensembled while staying small and efficient. Let's dive into how they pulled this off.
All right, let's dive into this paper. It kicks off by tackling the abstraction and reasoning corpus, which we'll call ARC from now on. ARC is a benchmark designed to test an AI's ability to reason from just a few examples. If you look at Figure 1, you'll get a great visual for this. Imagine you're shown a couple of before and after pictures. In one, a single blue dot turns into two green lines. In another, a little pixelated character becomes symmetrical. Your job is to figure out the rule and apply it to a new before picture. That's ARC in a nutshell. Now, the common way to solve this has been to treat it like a language problem. Researchers would convert these colorful grids into text and feed them to LLMs. But this paper argues that's missing the point. These are visual puzzles, right? So why not treat them as a vision problem? Their big idea is to reframe ARC as a simple image-to-image translation task. Think of it like applying an Instagram filter. You have an input image, you run it through a network, and you get an output image. The bottom of Figure 1 shows this perfectly. An input grid goes into their VARC network, and a predicted grid comes out. To do this, they use a standard vision transformer, or VIT, a powerful architecture typically used for natural images. We'll be calling it VIT from here on out. They train this model from scratch, using only the ARC data. This is a bold move, because it means the model has to learn all the reasoning patterns without the massive pre-training that LLMs get. Their approach, which they call Vision ARC or VARC, aims to show that a vision-centric model can compete with, and even beat, the language-based methods. So building on that idea, the authors emphasize that ARC puzzles aren't just visual, they're also physical. Think about it. Concepts like reflection, symmetry, and gravity are things we learn by observing the world, not by reading a dictionary. This makes their vision-centric approach feel very natural. They introduce a key idea here, incorporating visual priors. You can think of these as built-in assumptions that help a model learn, just like our brains have assumptions about how the physical world works. To do this, they represent the ARC grids on a canvas that can be stretched, shifted, and scaled. This teaches the model that a pattern is the same whether it's in the top left corner or the bottom right, a concept called translation invariance. This simple trick helps the model generalize patterns instead of just memorizing pixel locations. Next, they explain their training strategy. The model is trained from scratch on ARC data, but here's the clever part. When it sees a new, unseen puzzle at test time, it does a little bit of extra training on the spot, using just the few examples provided for that puzzle. This is called test time training, and it allows the model to quickly adapt to the new rule. And the results? They really speak for themselves. Their model, VARC, achieves an impressive 54.5% accuracy on the main benchmark using a relatively small model. This significantly beats other methods that are also trained from scratch. Just look at Figure 2, which shows off some of VARC's greatest hits. You can see it correctly solving some really tricky puzzles, involving things like connecting dots and completing shapes. It's strong visual proof that their method is working. Alright, so how did they actually build this? Let's get into the specifics of the setup. First, the paper formally defines the ARC problem, which is visualized nicely in Figure 3. You have a training set of 400 tasks, and a test set of 400 completely new tasks. For any given task, you get a few demonstration pairs of inputs and outputs. The goal is to learn the hidden rule from these demos and apply it to a new input. The key challenge here is that the rules in the test set are ones the model has never seen before. This is called cross-task generalization, and it's what makes ARC so hard. Next, they frame this as an image-to-image translation problem. They define a loss function, shown here in equation 1. This is just a fancy way of saying the model's goal is to make its output grid look as close as possible to the correct answer, pixel by pixel. It's a standard approach for tasks like semantic segmentation, where you're coloring in parts of an image. Here, instead of coloring in sky or tree, you're coloring in the solution to the puzzle. But here's where it gets really interesting. They introduce the concept of a canvas. Instead of working with the raw 30 by 30 ARC grids, they place each grid onto a larger, standardized 64 by 64 canvas. This is a great move for a couple of reasons. First, it allows them to use data augmentation, like shifting or scaling the grid on the canvas. This teaches the model that a pattern is the same regardless of its exact position or size, a critical visual prior. Second, it enriches the information fed to the VITs. Instead of each pixel being a single token, a patch on the canvas can contain a mix of colors, creating a much richer vocabulary for the model to learn from. This helps the model generalize better, instead of just memorizing. So we have the canvas, but what's the engine running this whole thing? Now we get to the heart of the machine. The authors detail exactly how they implement their vision-centric approach. First, they expand on that canvas idea with data augmentation, which is shown beautifully in Figure 4. They take a raw input grid, randomly scale it up by duplicating pixels, and then randomly place it on the larger canvas. This forces the model to learn the essence of a pattern, not just its specific size or location. It's a classic trick from computer vision that proves super effective here. Next, they describe the model architecture itself, which is laid out in Figure 5. They use a standard VIT. Here's how it works. The input on the canvas is chopped up into small patches. Each patch is turned into a token, which is just a vector of numbers. They also add a special task token, which holds the information about the specific puzzle's rules learned from the demonstration examples. This whole sequence of tokens is then fed into the transformer. The magic of the transformer is its self-attention mechanism, which lets every patch look at every other patch simultaneously. This allows the model to capture long-range dependencies and complex spatial relationships, exactly what you need to solve these abstract puzzles. After the transformer does its thing, a final predictor layer converts the process tokens back into an output grid of colors. Finally, they mention their two-stage training process. The first stage is offline training, where they train one single model on all 400 training tasks. This teaches the model a general-purpose ability to solve ARC-like problems. The second stage, which we'll get into next, is the test time fine-tuning for specific, unseen tasks. Okay, so that covers the first stage, the general offline training. But what happens when the model sees a brand new puzzle? This is where the second, and arguably most crucial, part of their strategy comes in. Test time training, or TTT. Once the model has finished its general training, it's ready to face new puzzles. When it gets a new task, it doesn't just make a single guess. Instead, it performs a quick, focused fine-tuning session using only the handful of demonstration examples provided for that specific task. Figure 6 provides a perfect illustration of this process. Take a look. You can see the model's prediction for a new input evolving over time. The first guess is basically a blank slate. But as it iterates and learns from the demos, the correct answer gradually takes shape, pixel by pixel, until it converges on the right solutions. It's like the model is cramming for a pop quiz, rapidly adapting its knowledge to the specific problem at hand. After this cram session, the model is ready to make its final prediction. To make the result even more robust, they use a technique called multi-view inference. They don't just show the input grid to the model once. They create hundreds of slightly different versions by randomly scaling and shifting it on the canvas. They get a prediction for each version, and then combine them through a majority vote. This is like asking a committee of experts for their opinion instead of just one, which helps smooth out any random errors. Finally, they mention a key detail for making TTT work with so few examples. They use data augmentation, like rotating the grids or swapping colors, to create more auxiliary training data on the fly. This gives the model more to learn from during that critical, fast-paced fine-tuning period. So we've seen the full method. But does it actually work? And more importantly, why time does it work? This next section is all about the results, and the authors do a great job breaking it down with a series of ablation studies. First up is Figure 7, which is really the main event. It's a bar chart that builds their model piece by piece, showing how much each visual prior contributes to the final score. They start with a naive baseline that scores a measly 26.8%. Then, they add 2D positional information, which helps the model understand where things are on the grid, and the score jumps to 43%. But the real magic happens when they introduce the canvas. Using slightly larger patches on a bigger canvas helps a bit. Then, adding random shifting gives another boost. And finally, adding random scaling provides the single biggest improvement, pushing the final accuracy all the way to 54.5%. This chart is the ultimate proof that their vision-centric ideas are the key to success. Next, they show that their choice of a VIT was a good one. Check out Table 1, which compares VIT to a more classic vision model called UNet. While UNet does okay, the VIT is consistently better, confirming it's the right tool for the job. Figure 8 further shows that their approach scales nicely. Bigger models generally lead to better results, which is always a good sign. Finally, Figure 9 dissects their two-stage training strategy. It clearly shows that you need both stages. The initial offline training provides a strong foundation, and the test time training on top of that is what nails the final prediction. Trying to do test time training from a randomly initialized model just doesn't work well. It's the combination of general knowledge and specific adaptation that wins the day. Okay, so the individual components are solid. But how does the final model stack up against the competition? Let's look at the system-level comparisons. This is where they put their VARC model up against the rest of the world. First, take a look at Table 2. It shows just how important their multi-view inference strategy is. A single guess gets them about 36% accuracy. But by showing the model hundreds of slightly different views of the same problem, and taking a majority vote, the accuracy jumps to nearly 50%. This is a huge gain and shows the robustness of the vision-based approach. Then comes the main leaderboard in Table 3. They compare VARC against three groups: LLMs, other models trained from scratch, and humans. When compared to other models trained from scratch, like the recurrent models HRM and TRM, VARC is the clear winner. Its 54.5% accuracy is a whole 10 points higher than the previous best, which is a massive leap. Next, they look at the LLMs. While some of the biggest models like Grok score higher, it's important to remember those models are orders of magnitude larger and pre-trained on the entire internet. VARC achieves its results with a tiny model trained only on the ARC dataset, making its performance incredibly efficient. But the most exciting result is the comparison to humans. Their single model is already strong, but when they create an ensemble by combining their VIT with a UNet, they reach an incredible 60.4% accuracy. This is significant because the average human score on this benchmark is 60.2%. They've effectively closed the gap to average human performance, which is a major milestone for the field. Reaching human-level performance is a huge deal, but what is the model actually times learning? To find out, the authors take us under the hood to see how it's thinking. They use attention maps, which are basically heat maps that show what parts of the input the model is focusing on when it makes a prediction. Figure 10 is a great example. For a task that involves copying colors, the visualization shows that to color a specific pixel in the output, the model pays sharp attention directly to the correct color in the input palette. It's literally learning a copy-paste mechanism. Figure 11 shows this from a different angle. For a task about drawing radiating lines, you can see the model's focus evolve through its layers. Early layers look at local details, while later layers focus on the global pattern of the radiating lines. It's learning hierarchically, just like we do. But the most mind-blowing part is in Figure 12. The model learns a unique task embedding, or a signature, for each of the 400 training puzzles. When they visualize these signatures, they find that similar puzzles cluster together. Tasks about coloring are in one neighborhood, while tasks about logical operations are in another. This is huge. It means the model isn't just solving 400 separate problems. It's learning an abstract map of asterisk how tasks relate to each other. This is a critical step towards genuine reasoning. Finally, the paper concludes by restating its powerful core message. ARC has long been seen as a language or logic problem. By daring to frame it as a vision problem, they've not only achieved state-of-the-art results with a much smaller model, but have also opened up a whole new and exciting way to think about and research abstract reasoning. Thanks for joining us today. Happy exploring together.